So another term we want to learn is size dimension and actual local size. So a size dimension is a dimension across two opposed or partially opposed surfaces, where an actual local size is a measured value of any distance across that section. So again, what's the difference between a size dimension and actual local size? If you were to think of measuring a piece of lumber and you had a 2x4 and you put a tape measure on the end and you said, okay, it's 2 inches across this way, or 1.75 inches by 3.5 inches. That is the actual local size at the end of the piece of the lumber. The size dimension on the blueprint, 2x4, is used for the entire surfaces that are on the, so they control the entire surface of a 2x4. But where you're only able to measure it is considered that actual local size. The reason that becomes important is that how many times is a 2x4 actually the exact same size all the way down the length of it? It may bend a little bit, it may be a little thicker in the middle, it may be a little bit smaller at the end. So those actual local sizes could change depending on where you measure that piece at. But the overall size dimension that's on the blueprint for it is relative for the entire surface. Features and complex features. So a feature, you'll hear me see this term a lot. A feature is any surface on a part. So if we're going to measure a round feature or a flat feature, it's any surface on a part. A complex feature is not something that we'll really get into much until our like week 7 class. That's when you're going to see multiple surfaces mesh together. So if you think about the handle of a video game controller, or you know, the area underneath a Windex bottle where your fingers go into, it's got a bunch of multiple curves, and we consider that in the GD&T world to be a complex feature. Where a regular feature is a diameter or a flat or a hole. Any questions so far?
Yeah.
Told you, riveting stuff, right?
Good stuff.
Regular feature of size. So what is a regular feature of size? So regular feature of size are something that contains opposed or partially opposed surfaces or elements. Again, thinking of back to that original PowerPoint slide that had a slot inside of a part. So you can drag something like a tape measure across it and you can measure it from side to side on there. That's a regular feature of size. A diameter, a length, a width. A regular feature of size will establish an axis, a center point or a center plane. And for those that don't know what those terms are, an axis is if you had a round component, a pencil, let's say. Pencils aren't always round, I apologize. But any round component, it has a center line to it or an axis of rotation that every piece of that outside surface is equidistant to, and that'd be the axis of that feature. Center point or center plane is for different types of features. A center plane would be for a square feature. So if you had a slot cut into something, there's a plane that sits in the center that's equidistant to both sides of the plane. That would be considered the center plane. A regular feature of size has a directly tolerant size dimension. They can be cylindrical, spherical, circular, two opposed elements or lines, or two opposed parallel planes. So it's a regular feature of size. So if you looked at your blueprint reading class that you took, probably 90% of the class, all the prints that you started with, would have been what we call a regular feature of size. Here's some examples of what regular feature of sizes look like. So two opposed surfaces. So in here we've got a slot cut inside of a part, and it's hard to see, but the areas that are shaded in red are what we're discussing here as the two opposed surfaces. So inside that slot are opposed. Two partially opposed surfaces, these two sides of the block, and what makes them partially opposed is they're not equal. They've got this chamfer on the edge of the part, so it's got an area where this feature is extended longer than this feature is. Circular part, so the little boss that's up on the top, the diameter of that boss would be considered a regular feature of size. A cylindrical part just by itself, the whole cylinder would be, the diameter of the cylinder would be considered a regular feature size. Or on this part, the spherical knob at the top would be considered a regular feature of size. So this cylindrical part would have an axis that would rotate about. These opposed surfaces would have a center plane. So there's a plane that determines the center or the midpoint between those two planes. Same thing here. On a circle, a 2D feature, you'll have a center point, and on a spherical part, you'll have a center point as well too. So there's always, if you notice, when we talk regular features of size, a lot of them, they're symmetrical. On the opposite side of that, what's an irregular feature of size? An irregular feature of size is a directly toleranced feature or collection of features that may be contained by different features. So one of the easiest things is something that you've all probably dealt with is if you think about the lug nuts on a tire or on a wheel of your car. Depending on your car, you might have 5, 6, 4, whatever, how many of those you have. Those irregular features of those circles, or the lug nuts themselves, are actually contained within a circle called the bolt circle. That feature, just as I'm showing here, would be considered an irregular feature of size. And why we call it an irregular feature of size is there's actually a diameter that all of these lug nuts, for lack of a better term, have to lie within. But that bolt, or that circle itself, is not an actual measurable feature. You can't take a tape measure and put it across there. It's a theoretical feature that is on the part to help determine where locations of other features are at. Whereas in this example, there's a hole going through the part. That would be considered a regular feature of size. Mating envelopes as well too. So as we talk through what the reason we need GD&T, it's always because of assembly. If you're not assembling something, you don't have to worry about putting any GD&T on it because it's not going to mate up with another feature. So actual mating envelopes are how parts fit together. You have features of size that may have several mating envelopes. We'll talk about that because it'll be actually part of your homework for this week too. Depending on what the lower limit of the tolerance and the upper limit of the tolerance is, will determine how your mating envelopes work. It's variable, derived from the actual part. So if you put a lug nut onto the car, and it's a little bit bigger than the rest of them, it's going to be a little bit harder to get that wheel on there. You got to be more perfect about assembling that wheel onto the car than if all the lug nuts, or the studs, I'm sorry, were a little bit smaller. They're a little bit smaller. It gives you a little bit more play to get that wheel onto the car. So here's an example of what mating envelopes look like, right? So in the first instance, all the way on the left side here, and ignore the GD&T and the tolerance and everything else, this is what is on the drawing. This is what the expectation is. Exaggerated, this is what we get when we actually make the part. So maybe it's got a little bit of a bend to it. Maybe it's crooked. But once it's crooked or it's got a bend on it, the pin, so let's imagine that this is just a cutaway of a piece of the wheel on your car. And these lines right here represent the stud that sticks out from the wheel assembly inside on the car. This hole you might take a tape measure or a micrometer or a dial caliper and measure across here, and you say, hey, great, it's within tolerance. It's at 9.45. It's right in the middle. Perfect. But when you go to assemble it, it won't go in because the hole is crooked or bent on her. So what we end up with is a mating envelope that is smaller than the feature of size allows. We've talked a little bit about axes and center planes. So axis is a straight line about which a geometric object rotates. A center plane is a theoretical plane about which a geometric object is equally disposed. So fun terms, but an axis is the center line of a part. The center plane, the axis is the center line of a round or cylindrical part, and a center plane is just a midpoint between two flat faces. So here's some examples of axes and center planes. So right in the center of this hole is an axis that goes straight down. So it would come out of your screen as you're looking at it and go out through the back of your computer screen on the other side. Not necessarily worried about the datum structure and everything like that here, just to show you what that axis looks like. Now this feature right here is actually a square cutout through the part, and we show a center line on here, but the feature itself is actually a center plane. And does anybody, well, I guess maybe I should back up and talk about what a plane is versus a line. A line is, you only need a single point in space to create a line, right? Once you create that point in space, you can have a line going in whatever direction through that point. In order to have a plane, you need to have 3 points in space. So the front face of your computer monitor would be considered a plane. The back of your computer or the tabletop would be considered a plane. Axes are a little more hard to define. I'm sorry, center, yeah, an axis is a little more harder to visualize, but it's the center of rotation of a part. So anybody that's worked on a lathe before or used a cordless drill as the drill spins around the axis. So I thoroughly confused everybody yet?
You're getting there.
You have to forgive me. I love teaching this class because I get, you know, some of the basics of it, you forget about, and I forget about. And so if I am skipping over those too fast, you guys have to let me know, because I'm going off the assumption of, based off of some of the previous classes or your work experience, that some of this stuff might be some repeat information for you. But if it's not, let me know. We can figure out a different way to explain it. Two terms that we'll get to use a lot in GD&T is called maximum material condition and least material condition. So if a feature that we have on a part has a tolerance on it, the largest maximum material condition changes based on whether it's an external feature of size, so the outside of a shaft, or if it's an inside feature, an internal feature of size, like a hole diameter. The way to think of maximum material condition is when the part weighs its heaviest. So let me try something here. I'm gonna share something. But everybody's screen just changed to white?
Yep.
All right, so this is the whiteboard that I get to use a little bit in class. So if we were to look at a part, and let's just say I'm gonna draw the left side of the part, and it's gonna have a hole going through the middle of it. I can draw a heck of a lot better using CAD than I can by hand, so don't judge me I got a horrible handwriting too, so that's why I type everything up. And if we were to look at the right side view of the part, and let's just say it goes like this. I'm gonna draw another diameter on here that represents, so let's see if this works too. So this horribly round, it's perfectly round. Okay, on my computer, it's perfect round. This value right here associates with this diameter up here. This diameter here associates with this feature. And then I'm going to draw hidden lines going through the center of the part. Let's see here. So if we were to want to know what's an internal feature in size and external feature of size, these diameters right here would be considered external. See how good my handwriting is? This would be considered another external feature of size. However, this hole right here would be considered an internal feature. Easy, right? Now, if that hole was 0.5 inches in diameter, and we were to say you had a tolerance of plus 0.01 minus 0.01. Everybody following along?
Yeah.
If I wanted to know the maximum material condition for that hole, at what point is the part its heaviest? What size would that hole be when the part is at its heaviest?
It's least material condition.
490,000.
Not too.
499,000.
490. So that's our limits go from 510 to 490, right?
Yeah.
So if we wanted to know the part is at its heaviest,
The hole would be the smaller.
the hole would be the smaller, right? So, and the hole in an internal feature, that 490 would equal maximum material condition. We think of, sorry, go ahead.
Wouldn't that be 499 and 501? No, never mind. I lied.
No, don't worry. You made me think, Dave. Thank you. So I do that a lot too. So catch me on my math. It's easy math that gets me sometimes. So
Heather,
sorry, go ahead.
said Heather would kill me.
So when the part's at its heaviest in an internal feature, the hole is at its smallest size. It's got the most material on it. Now, if we were to go over to the external feature here, let me change my color. And if we were to say that this diameter here was 0.750, it was the same tolerance zone. What's the upper limit? Dave, you want to do the math on this one?
No.
0.760 would be the high. 0.740 would be the low, right? At what size is the part at its heaviest?
The bigger one on this time because the external. So 760.
So 760, right? So 760 for an external feature would equal maximum material condition. Makes sense, right? Maximum material condition means the part is at its heaviest. So on outside features, when it's at the upper end of its tolerance, that's when it's at its heaviest. For internal features, when the part's at its small end of its tolerance, that's when it's at its maximum material condition. Any questions about that one? Maximum material condition?
No.
Perfect.
Pretty good.
One of the homework assignments, actually the first one for chapter 5, that's all it is just there's a print inside the book. They've got a handful of dimensions on there. What I ask of you is to take each one of those dimensions and define out what the maximum material condition and least material condition is for those dimensions, right? And you're going to do it following along just with this same type of structure. And if there's just one thing I can stick in your head, maximum material condition is when the part weighs its most. Least material condition is when the part weighs its least. If you think that way when you do that assignment, and you try to, and you're understanding, you're taking a look and saying, is it an internal feature or is it an external feature? It'll be a really easy assignment for you. On the opposite side, right? If an internal feature at its smallest size is maximum material condition, then at the largest it is would be considered its least material condition. Now, when the hole is largest like that, that means we've got less weight on the part, so that's its least material condition. But on the external size, when the dimension's at its smaller, we have least material condition on that side. Again, some of the repetition, some of that little homework that'll help you grasp this a little bit more. Perfect. Go back to the PowerPoint. Any questions before I jump back in the PowerPoint? All right, cameras are on, people aren't sleeping, so I'm doing all right so far. All right. Awesome. There's another term that pops up every once in a while, and it's called regardless of feature size. So in the GD&T world, we'll talk about when that shows up, but regardless of feature size is in the absence of the call off for maximum material condition or least material condition. So what'll happen later on when we dig into some of the true GD&T, they'll have a call out where they'll say, hey, this tolerance, this geometric dimensioning, or this geometric tolerance that we're putting out there is only applicable at the maximum material condition. So again, thinking through that tire and that lug nut, right? Trying to fit out, or the stud, I keep calling it a lug nut, I'm sorry. The bigger that stud is, the more perfect that position has to be in order to get that wheel on there. The smaller it is, you get a little more wiggle room. So when that stud is at its largest or its maximum material condition, it's got to be spot on exactly where it's supposed to be. Otherwise, that wheel is not going to go on there. The smaller it becomes, the more wiggle room that we have in there. I don't know if you can see me as well as the screen, but I'm doing a bunch of hand movements too. But regardless of feature size, it's really, it's just a term to understand. It's not going to be applicable. It's not going to change the way that we do anything down in the future. Patterns. So 2 or more features to which a locational tolerance is applied would be considered a pattern. And all these methods that are in bullet points here are just ways that you can see it called out on a blueprint. We can apply a geometric tolerance to a pattern, which we'll talk about too as we get into each one of the GD&Ts. One chapter down. Any questions on those terms? For any of you that had a little hard time following along too, that chapter 5 in your book, which is only 10 pages long or so, has got everything that we just talked about in there as well. All right. So if you touched base with this in your blueprint reading class, this should not be completely foreign. These are the GD&T symbols that we'll be going over for the next 7 weeks. There's 14 of them.
Hey, Tim, 1 second. I can't see your screen anymore.
Oh yeah, did I lose it? What happened?
I can. I can't see a screen either. Well, now I can.
Oh, there you go.
There you go. Thank you.
There you go.
There you go.
All right, see, it's all technology. I got an iPad going for whiteboards. I've got computer screens. Thank you for letting me know, guys. All right, here's the symbols. So everybody can see the symbols now?
Yep. That's all good.
Perfect. So really, this is also in the book as well too. I'm looking up the page number right now. Page 64 in your book. The way that we broke the class down too is by kind of form, profiles, locations, orientations, and runouts. So that as we teach the symbols, we're going to group them together as such. So next week, we're going to start with these 4 symbols: straightness, flatness, circularity, and cylindricity. And over here, you can see the symbols as they relate to the characteristic: profiles, locations, orientations, and runouts. The profiles are probably the most advanced, and if you look at the syllabus, that's why we're kind of putting those more towards the end of the class on there. The symbols themselves really are the way, it's like reading a different language, hieroglyphics or something like that. The way to communicate which characteristic that you're calling out on your blueprint. Make sure. So let's talk about the 5 geometry attributes of a feature. And again, this kind of relates if we look back here to, if you look at these categories, you have them on your book too as well, page 64. The 5 geometry attributes of a feature are the size of the feature, the location of the feature, the orientation, the form, and possibly the surface texture. Surface texture is not going to relate to us in GD&T, but you'll see call outs on blueprints for what the surface texture of a part needs to be. Again, depending on what field or if you're working in manufacturing at this point in time, you might not have been exposed to the surface texture much. But size, location, orientation, and form. So again, size, how big is it? Location, where is it at? Orientation, is it crooked or is it in its right location? And is it in its proper shape? So if I'm using a bad example with tires with studs, let me know. But so if we think through that feature and we want to talk about just one of those studs when you have to put a tire on, if that stud is too big, the tire won't go on. If one stud is in the wrong location, that tire won't go on. If one of those studs is too crooked, that tire won't go on. And if one of those studs is so oval shaped, that tire won't go on, or wheel, sorry. So starting to introduce the GD&T language, what we have is called the feature control frame. The feature control frame is divided into these 4 components. So let's take a look at it here with some real feature control frames. So this rectangular box right here in GD&T terms is called the feature control frame. The first compartment, it always contains one of those 14 GD&T symbols on there. The second compartment, always contains the tolerance information. And if you notice, there's a little bit of extra information in here with this diameter symbol and this M, which we'll talk about further along in the class. The last 3 boxes are what we call datums, and that's something else that we'll go over in a subsequent class on here. So you put all this together, and this is what we call a feature control frame for defining what the geometric dimension and tolerance is for a certain feature on a part. Feature control frame, it applies to a surface when it's placed on the drawing and attached to the part surface or its extension line. And it applies to a feature of size when it's placed on a drawing and is associated with a size dimension. I think I've got an explanation here. So if we take a look, believe it or not, these are the exact same symbols, the exact same part, right? Except in this one, the GD&T feature control frame is attached to this extension line. And in this one, the GD&T is attached to the dimension. They have 2 different meanings. In this particular one, this perpendicularity applies only to this face. And in this one, the perpendicularity applies to the center plane between those 2 features. So not something I expect you to remember, but something to understand, especially if you get into a point where you're writing programs for inspection routines on a coordinate measuring machine, 3D scanner, ferro arm or something, a portable CMM. How you define that feature could show it to be in tolerance or out of tolerance. So if you interpret them as backwards from each other, you might get lucky, it might be okay, but one of the things you want to make sure you're always doing is it will never work in your favor if you inspect that part differently than what your customer inspects that part as. When they come back and tell you that your part's out of tolerance and you're looking at it, the part's in tolerance, getting to the root cause of the problem is rather difficult. And a lot of times we see that as the interpretation of GD&T based on the location of the feature control frame. Continuous feature modifier, I'm going to really gloss over this. This is something that you're never really going to see in GD&T world, but if you take a look at this part, it's got a bunch of steps that break up those surfaces. So in the literal world of GD&T, without this feature on here, this symbol only applies to the first face. Same thing with this one here. But by putting this continuous feature on here, they're saying it goes across absolutely everything. Again, not something we typically see. It's very uncommon to use it. Any questions?
Would you ever see it called out with both the center line and the surface edge, like in this slide here? Would you ever see both of those on a blueprint?
I never have. And again, when you go back to what's the intention for needing that surface to be perpendicular, right? Depending on what this part is used for, and this is something I had just drawn up in SolidWorks to use for an example, but let's say that this feature right here is mounted to a table and something rolls back and forth inside that slot. Having the center plane be perpendicular is probably more advantageous at that point, because if the top and bottom start to get a little out of crooked from each other, you might bind up at certain areas. If this feature right here, if the whatever rolled back and forth only contacted this face, then that's the reason you would call it out just on that surface. So if somebody did and put it on both those, put it in both locations, I would definitely have a phone call with the engineer at that company and say, help me understand what your intent is here, because I don't think it's necessarily breaking any rules from a GD&T perspective, but it would definitely be out of the norm. Great question, Dave.
So would one of them be more important than the other?
If both of them showed up, no, you'd have to control both of them just as within the tolerance zone.
If the lower tolerance, let's just say the one on the bottom, there was a roller that rolled back and forth across the bottom of that, and maybe the upper side of it controlled any slop in it, or I don't know, but I'm just trying to, I'm just trying to understand how it might be there or not.
And what we don't have listed on here either is the tolerance for the 0.500, right? So you can have it to be 0.500, and it could be really loosey-goosey tolerances in this thing. One piece might be 0.475 and the next one might be 0.600 based on what the tolerances are, but they're perpendicular and they might not work the same, right? So the other piece of when we're designing a component, we'd have to think about how tight do we need that tolerance to be for the feature of size, which is the 500, and then how do we need to control its form with perpendicularity. So in the end, they both have to be in tolerance. So you can't have one and not the other.
Okay.
Does that help you out, Dave?
Yeah.
All right.
In this particular feature, what does it want it to be perpendicular to?
Datum A. So datum A is back here, and
Oh, okay.
yeah, and again, we're getting a little bit of ahead of ourselves, and it's kind of the way the class rolls. We build a little terminology, and then we talk a little bit about GD&T, the ones that don't require any datum structures, and then we talk about what a datum is and how it applies to everything too. So, great questions though, and I do encourage everybody to ask the questions, because chances are you're not the only one with that question.
So the modifier on there is referring to the, what is it, 10 thousandths off of A,
Mm-hmm.
the datum A.
Yep. So the way you would read this, and again, kind of getting a little ahead of ourselves though, is that the feature control frame reads perpendicular within 10 thousandths to datum A. That's how you would read that. Perpendicular within 10 thousandths to datum A. And 10 thousandths, that's the machinist way of calling that out. So if the weatherman would call that, I always forget what they would call it, 10 hundredths or something like that. But perpendicular within 0.010 inches to datum A. if we need to go back at all. So believe it or not, with GD&T, there is actually a set of dimensioning rules. There's 16 of them, and they're automatically invoked when ASME Y14.5 is applied on the print. So you guys probably actually learned about ASME Y14.5 a little bit in your blueprint reading class. What's nice about that is, and I'm calling this GD&T, this is more for the standard dimensioning, but is having that set of standard dimensioning rules has somebody to break the tie, let's say, right? To break that interpretation, you can go back and you can open up the standard and say, this is what the standard says, so that's how we invoke it. The other reason is that you're creating a drawing that's got dimensions on it, and then you're asking somebody at a different location to make those parts for you, typically. I always say you find out how good your blueprints are when you ask somebody else to make those parts for you. It's really easy to make a blueprint that doesn't have all the dimensions on there or isn't toleranced correctly, but you know that it needs to fit pretty good, or you know that this needs to have a really shiny surface finish on it. But it's just tribal knowledge that's been gained over time. Once you dimension your blueprint accurately, then anybody can repeatedly make that part to the same tolerances and same standards that you would make that part to. Something that we'll refer back to a lot called rule number 1. Dave, this might be kind of what you were alluding to. Is there anything that takes precedence over something else?
Right.
So this is a mouthful here, but this is the way that rule number 1 is stated. The form of an individual regular feature of size is controlled by its limits of size. So what that means is that, let's go back to the whiteboard. Let's share this again here. So let's say that we have a diameter, and we call out that diameter to be, we'll stick with some of the same sizes, 0.500 plus 0.010 minus 0.010. So on that, based on those tolerances, we have a outer limit of size. I know that's perfectly round on your computer, so.
That's a great circle.
Right.
Perfect.
And we have an inner limit of size. At least I'm consistent. It's always sticking to the right there. So on that outer limit, well, let's fix, since I got the color here, that inner limit is 0.490. That outer limit is 0.510. And so it's perfectly fitting that I didn't draw those things as round as they should be, because what we talk about in rule number 1 is that, let's say, and I don't have to exaggerate much because I didn't draw it perfect, that it looks that oval shaped. And if you were to measure it across this side, let's say you get 0.515, and you measure it across this side and you get 0.485. If I've been to a lot of places where, let's just say, the emphasis is getting parts out the door, not necessarily the right parts out the door all the time. So I'll have somebody come to me and say, well, if you average those two, it's 500, so that's a good part, right? No, it's not a good part, because whatever that hole is that pin's going to go into, this 515 feature, that size right there, is not going to fit into the hole. It's going to be too big. So because what happened is the form of the feature is not correct. It's not round, creating a different size here and a different size here has affected what we look at as the tolerancing. So that, back to that rule number one, let me see if I go back to my share screen. I do it right? Back to the PowerPoint?
Yep.
The form of an individual regular feature size is controlled by its limits of size. So back to the whiteboard again. We'll go back one more time. Erasing, that's something new. Oh no, does it keep it back? Nope. It erases it every single time. Sorry. Is that when we have that outer limit, oops, that's not what I want. That outer limit, ooh, that's a better circle. The part can be out of round, and we have an inner limit here. You can have an oval shaped part, but it has to fit within those inner and outer limits. That's what rule number one states. Go back to sharing screen here. All right. So what that does is it ensures that the regular feature of size will assemble with another piece, just like we talked about if it got too far out of round. So rule number one, regular feature of size is controlled by its limits of size, the form of a regular feature size. So what are those requirements? The surfaces shall not extend beyond a boundary, which is considered maximum material condition. And we talked a little bit earlier about what maximum material condition is. It's the upper limit of the tolerance or the lower limit of the tolerance based on whether it's an internal or an external feature. Somebody got a question or we good? Awesome. Where a regular feature of size is produced at maximum material condition, it must have perfect form. So back in the case of that drawing that I beautifully drew up for you in different colors on a whiteboard, if we produced a part all the way at 0.510 diameter, which is the upper limit of the size, that part has to be perfectly round. If it's not, it's going to have points that are outside of the maximum material condition boundary. Local variations in form equal to the amount of the difference in size from maximum material condition is allowed. And rule number one only applies to individual regular features of size. So back to a irregular feature of size or regular feature of size, you can't apply it to the circle that's on a bolt circle. You can only apply it to the diameter that's in one hole that's in the bolt circle. Somebody pointed out, it is on page 74, I believe, in your book, is the actual, the true definition of what rule number one is. So we got that right. Double checking the book. All right. So again, kind of taking a look at what does rule number one look like in real life. So if this is what the drawing looks like, we've got a U-shaped piece of material with size on the outside. The rule number one boundary is the high limit or the maximum material condition on the outside feature of that part. If the part's got such a bend inside of it that the part is going to be greater than the boundary, we have a bad part, right? The other thing too is it can't go tighter than the inside of the least material condition boundary as well too. We'll talk a little bit about gauges, right? So imagine that this U-shaped channel had to fit into something else that was already pre-cut into a part. If it was bent too much, no way is it going in there. Again, where does rule number one apply? Individual regular features of size. So items like this is a regular feature of size. Irregular features of size, like a bolt circle pattern, the rule number one does not apply. And rule number one only controls form. It does not control location, orientation, or alignment between features of size. Only exceptions to rule number 1 is the feature of size on a non-rigid part. I don't know if it's showing up pretty well, but I've got a clear plastic tube in the bottom left corner. So they'll call that tube, they might say it's 2 inches in diameter, right? But since it's squishy, you can squish it back into shape on there. So it's not, you can't put that rule number 1 attached to a flexible part like that. And then stock sizes or raw material sizes is also another area where it does not apply to. I'm going to skip over the independency symbol. But how would we verify size dimensions? For any of you that have actually worked in a manufacturing environment, you might have come across a go, no-go gauge. And what a go, no-go gauge looks like is something like this, right? Where what we can do is we can check the feature size for variation or for violation, I'm sorry, of certain limits. So in this case, it's a pin gauge. So in that instance where we called 0.510 to 0.490, our no-go gauge might be 0.511, just 1/1000th of an inch over the high limit. And our go gauge would probably be the actual 490 itself. So if we stick that go gauge in there and it goes all the way down, we're good. If we stick that no-go gauge in there and it goes in, we're not good. This instance right here is for checking the outside of the same part, right? So you might have a 490 right here and a 510 up here. So if the part goes through, you're good. If it won't go in, you can run into problems. Or if it goes into here, I'm sorry, you'll run into a problem. Quickly wrapping through the last chapter. Any questions so far again?
No, not yet.
All right. I apologize if this is a lot of information. One of the nice things about being in class with everybody is I get to see if you're fidgeting in your chair, having a hard time, and we can stop and talk about something a little bit more. But again, feel free to touch base with me outside of class if you need some additional help. So other GD&T concepts, we'll talk about boundaries, inner and outer boundaries, virtual condition boundaries. It's a topic that we can read about, but we're not going to discuss it much here. And again, those boundaries affect how parts are going to assemble. You're starting to see the theme here. I've said it a lot. This is all about parts that are going to assemble together. Inner boundaries of internal features of size create that worst case boundary. Inner boundaries of external features of size are worst case boundaries generated by the least material condition. Again, a lot of crazy information here that you guys will read a little bit about between the next class, and then we start to get to apply it a little bit when we start talking about some of the tolerancing that goes together with GD&T. Skip over those. The feature control frame, again, as we talked about, where does it apply? Applies to a feature, and it applies to a size dimension of the feature depending on where it's located on the drawing. Does not affect the worst case boundary of the associated feature size if it's applied to a feature, but it does affect the worst case boundary if it applies to a size dimension of the feature. So again, is it attached to the dimension or attached to the extension line? Changes the way we interpret it, and this plays into that as well. Worst case boundary with geometric tolerances. There is a modifier called a maximum material condition modifier and a least material condition modifier. We'll see those as we get onto some of the GD&T later on, but that's where some of the important information comes from, of why we have to understand what a maximum material condition is. We actually get bonus applied to some of our tolerances depending on whether or not these things are used. So again, here, if we talk about what worst case boundary formulas look like, the internal worst case boundary is maximum material condition, and external is, how am I reading this wrong here? Inside boundary equals maximum material condition for an internal, and outside boundary equals maximum material condition for an external feature. And it's just redundant as we're talking about it, different ways of saying it, but understanding, again, why are we putting GD&T in here is to make sure that things mate together properly. Skip over these two. This is the real reason why we talk about these boundaries and the maximum material condition and least material condition, is because we get something called a bonus tolerance. And that's an additional tolerance for the geometric tolerance, and it's only permissible when you use maximum or least material condition. The actual amount of the bonus tolerance is the amount the actual mating envelope departs from the maximum or least material condition. And again, we talked about it a little bit earlier where we said, all right, if you have 5 studs on your car that you need to put your wheel back onto, and 4 of those studs are at 3/4 of an inch, and 1 of those studs is at 1 inch in diameter. You're going to have to be perfect when you put that wheel back onto that car, because that 1 stud is a little bit bigger than the rest of them. If they're all at 3/4 of an inch and the hole in the wheels are at 1 inch, now when you go to put that wheel on, you got a little bit of wiggle room when you go to put it onto the car itself. And that wiggle room can be taken up by that those studs don't have to be perfectly 60 degrees apart or 45 degrees apart. They can have a little bit of angle difference on them because they're smaller than the holes in the part. And that's what we call bonus from a GD&T perspective. The bonus is I get to be off a little bit. How much? Depends on how big the studs are on the car. If they're a little bit bigger, less bonus I get. We'll talk about, I'm gonna go back to the whiteboard real quick and see if this, draw it out. So when I'm talking about studs on a car wheel, let's just say we've got five holes in the center of the wheel itself. If these are 3/4 of an inch and the hole that it mates up to is 1 inch, apologize for my handwriting, that means that the position of this can vary a little bit by roughly 1/8 of an inch each way, right? It'll allow it to shift over, because if it's 1/8 of an inch all the way off to the right, it'll still go inside that 1 inch hole. If it's 1/8 of an inch off all the way to the left, it'll still go into that 1 inch hole. If it's perfectly centered, it'll go in there too. That would be ideal, but we need tolerances for manufacturing. Back to the PowerPoint. Skip these over too. I'm not going to talk about virtual conditions. It's a little bit, some of them go over pretty well, and some of this stuff is a little tough to teach over the computer. That's it for the lecture piece of tonight. Exciting stuff, overwhelming.
I think the overall concept makes sense.
It can be pretty overwhelming at first, and that's why those that can ask questions, please do, because as I'm saying, there's 29 people in the class. Chances are somebody else has the exact same question that you do. If any of you think that this, if I'm moving too fast, or it's a little more in depth than we need to go, please give me the feedback. I can do what I can to try to cover less in-depth pieces of the topic and try to get more width of the topic for everybody as well.
Sounds good.
Any questions?
Question, sir. Yeah.
Somebody's got one? No.
Well, there's two of us.
Okay.
I just had a question regarding the syllabus. If that's something that might change, or can I just move forward if I can? And
Yes, by all means. I think I opened up most of the homework assignments, so you guys can move forward. You can read ahead. By all means, PowerPoints. I'm going to create PDFs and make them available for everybody as well. Some of you might have been exposed to this stuff for quite a while, and you'll catch on to it quick. And other people, this might be the first time you've ever seen this before, and are going to close your computer up and go, "What did I sign up for? It's supposed to be nice outside. I'm supposed to be drinking beers on the patio, and here I am doing this." So, but rest assured, the way that I operate is I want to make sure you guys get an A in this class. So I'll do what I can to help you out. If you put the effort in, if you do the homework assignments, if you're falling behind and we're talking about it, we'll make sure that you do well in the class. So every answer for every homework assignment is inside the book that you have. All the homework comes out of here. I'm going to reconfigure what the final project would look like as well. In an engineering world, you're never alone. You're working with a group of people. This concept of everybody being home and have to e-learn kind of kills that ability for everybody to work in a project environment. But maybe we can get creative and allow you guys to do that through Zoom or through other avenues as well too. But I want to make sure that the project is fair. I want to make sure that you're learning the topics. And at the end of this class, I want you guys to feel comfortable talking to somebody about what GD&T is on a print and having your interpretation be accurate.
Tim, what are you thinking of the project may be? Do you have any idea yet?
The final project, the way I had it was what we would do is I had a bunch of models of skateboard components, and as a group I had drawings built for those skateboard components, and I have a problem statement built together saying that components X, Y, and Z are manufactured at one facility and products A, B, and C are manufactured at another facility. We have a quality problem where the products don't always assemble together properly. And what is the interpretation that's happening between the two sets of drawings, and how do we use GD&T to make sure that they're all going to assemble together? So as a group, what you were in my past classes doing this, we would pass it out. I would be your lazy boss sitting at the front of the classroom doing nothing, and you guys would work as a team to go through the problem statement, assess the situation with the blueprints, determine why they're not going together, and then start to use the tolerancing methods you learned in your previous classes, plus the GD&T you learned in this class to come up with a solution. And I'm less concerned about the math behind it all. So if you were to say that you wanted to have, the hole had to be perpendicular to this face, I don't care what number you pick. I'm more concerned whether or not you pick the right symbol and put the feature control frame laid out properly. That's the main concern. So the biggest math you're going to do in this class is plus or minus.
Okay.
So the middle project that I'm trying to think of right now, because again, I just want to create a little more engagement. I know this is a very dry subject. I'm trying to working up how I want to put it together, but I'm thinking of something along the lines that I want you to find something in your house that you've put together that just did not go together the way that you would hoped it would have. Maybe you bought a new desk from Walmart to get ready for e-learning, and as you go to put it together, the screw doesn't want to go in the hole when you go to put that last one in there, and then to start thinking through what could have possibly happened, and how would as engineers or as manufacturers, how could we have done something better to improve that? How could we have communicated that better? So I'm still working that through a little bit, but I'll put that out there for us once I get it laid out. What I do want to share with everybody real quick is, for those that haven't been on Canvas, let me open it up here. So this is the syllabus for the class. So for tonight, everything that I've got laid out here, except for these projects, are all to be done through Canvas. The first one, the Chapter 5 application problem, is you'll submit a Word document for that, but you copy and paste this. Go to problem number 5 in your book for Chapter 5, and it'll explain everything as far as what you need to fill into these tables here. You'll be able to submit it to a file upload, Word document, Excel document, whatever you choose. I'll be able to take a look at it, and you'll put the information in there. In the past, this has not been a huge homework class, other than really I've asked people to do the reading. What I'm typically used to teaching is people that have worked a 10-hour workday, and then they're coming into this class at the end of the day. And I know the last thing you want to do is have a absolute ton of homework on top of making dinner for the kids and helping people with homework. So, but I do want to make sure you learn, and reading it's going to be the best way for everybody to learn. So for next week, we'll ask you to do the homework from chapters 5, 6, and 7. Read the chapters as well too. It's probably only about 20 pages long. It'll hopefully help further ingrain into everybody what we're talking about tonight too, but it gives you a second chance to relook at it and rehear it again too. So that's all I got for tonight. If there's no questions, I'll stick around if anybody needs to stick around at all, but you're more than welcome to start logging off.
All right.
Thanks, Tim. Thanks, guys.
Thanks, Tim.
Have a good night.
You
Have a good
too.
one, Tim.
Thanks, Tim.
Mary,
Have a good
Amy,
evening.
if you guys have any feedback for me, let me know.
Tim, I'll send you an
On
email.
Memorial Day weekend.
Okay.
Hey, Tim,
Yes?
I did send you an email regarding the book.
Okay.
I remember buying one last semester. I misplaced it. I'm going to try digging through it. But if
Okay.
I can't find it, I did send you an email about working something out about either a online copy or acquiring another physical copy.
I tried to see, I was hoping that they would have an online copy as well. So, those that did have to buy the book wouldn't have to buy it, but I couldn't find an online copy, although I think Amazon rents an online copy for $25. But
Only if you have a Kindle.
only if you have a Kindle. Can you download the Kindle app? So,
You can download it. I've got the electronic version and the book both. The electronic version is only online. It unlocks it for 6 months. And you got to have a login. You buy the login through the bookstore, and you can look at the book. You can't download it, and you can only print 97 pages or 100 pages. You can't print the whole book. So, but it is and it's searchable. You can go in there and search inside the electronic book, but it doesn't allow for doesn't allow you to print the book.
okay.
But you can buy that straight. You buy that straight through, and it's $18 or $19 at the bookstore or something like that.
Okay. Rick, I'll email you back. I'll send some more information over to you as well. I think
Awesome.
Rick, I think I had you in a metrology class once before, right?
Yeah, I think it was that one.
Perfect.
Because I remember having something for GD&T, and I know I still have it. It's just finding it, whether or not it's in storage,
Okay.
in my garage, or in a file I have in my room.
Mm-hmm.
It's finding it, and in case I don't find it, I figured I consult you now instead of in a day or two when I didn't find it and it taking longer to get. So But yeah, have a
Do you
nice
know what
evening.
vintage or something for GD&T is?
I'm sorry, say it again, Francis.
I was asking him what vintage his something for GD&T
Oh.
is. Because it's changed a couple of times over the years, in decades.
This is book 3. There's also a 9th edition out there, but it's not by the same author. This
That
is-
wasn't what I was referring to, but okay.
Yeah, if we
Well, I
stick with,
understand. I'm just saying there's a whole bunch of these books out there. There's a 9th edition of somebody's, and then there's this one, which is the 3rd edition. 2 different authors, 2 different books. I'm sure they cover a lot of the same things, but it's not going to have the same problems. You know, it won't have the same, go take, problem 5 and give me the 6 or 7 or 12 numbers that you need to off of that.
yeah,
Well,
Don't worry,
actually,
might
the
be different.
specification has changed over the years, from the mid-90s up through the early 2000s, up through now. So as the specification has changed, so the books are changing.
Okay. Good job, Tim. Thanks so much, buddy. I appreciate
you.
it.
Have a good one, Tim.
me too.
I always stay on late just in case there's something else I need to know.
No worries.
All right, cool. Is there anything, the only thing I was thinking of, Tim, oh wait, these guys are you guys done? Salvador and,
You guys have any questions?
I don't understand.
I don't think so.
No.
I don't know names. We got Papaka and Salvador. Do you guys have any questions? Or
No,
if not, you guys are more than welcome to
it's fine.
log off.
All right, we're. I guess that's when you know people are fidgeting or they're not there.
Yeah.
So the only thing, Tim, when you post these recordings, is it you talking or just the PowerPoints?
It's this whole thing. So actually, I forgot to stop the recording.